So the assignment sheet for day 17 was a little on the long side. A lot of groups didn't quite finish, so I just wanted to go over the answers or how I would go through these questions. Because it was a little bit long, I adjusted it for the second section. So if you're in the second time slot, your problems will look a little bit different than this. I took out a couple of them for time's sake, but it's worth noting that I'm using the first section's questions for this. Okay, so we've got a basketball player shooting 80% of her free throws. In this version of the question, what we're asking for is, in the situation where she shoots 2 free throws, what is the expected value for the number of shots made? And the hint here was make a tree diagram. You didn't have to make a tree diagram for this, but let's do it that way. All right, so there's an 80% chance that the first shot is made and an 80% chance that the second shot is made, which means that there's 20% chances of misses. And we can find the probability of ending up at any one of these end nodes by multiplying through. So in this case, 0.8 times 0.8 is 0.64. That is the situation where 2 shots were made. Similarly, we've got a 0.16. That's the probability of making the first one, missing the second. 0.16 for missing the first, making the second, and 0.04. So if we also write down the number of shots made, we can form a table. We can then use this to find the expected value. So the expected value of a random variable, so in this case this is the number of shots made, and this is going to be equal to the probability of a certain outcome occurring times the value of that probability, of that situation. So 2 times 0.64 plus 0.32, so I'm combining these two terms. 0.32 times 1 plus 0.04 times 0, and this should come out to, I believe, 1.6. To find the standard deviation, we want to take the variance, or it's easier to first find the variance. And what we're doing here is we are adding up all of the terms where we are finding the difference between a particular value and the mean, a particular value, and what we just determined that the expected value was. We're squaring that and multiplying by the probability, and then doing this for the rest of the terms, which I believe ends up being 0.32. And then if we want, what we really want is the standard deviation of this distribution. Well, for that we're going to end up square rooting this. This is the square root of the variance, which should be 0.56 something. All right, so next up we're asking what happens if we do this a total of 3 times. And so the hint here was to not make a tree diagram. We don't, since she's taking a total of 6 shots, that would be quite a lot of different nodes. It's just not worth dealing with that. Since all we really care about is what the mean and the standard deviation is, we can use the fact that the expected value, or the mean, is additive, and the variance is additive. So if x is the number of shots made when you're shooting twice, then what we're after here is a total of x plus x plus x, or 3x. Well, the expected value of 3 of these instances, well, is just going to be 3 times the expected value of one of them, which I believe is 4.8. The variances also add, so the variance of doing this 2 shots a total of 3 times, so a total of 6 shots, is going to be 3 times 0.32, also known as 0.96. And again, if what we're after is actually the standard deviation, we're just going to take the square root of the variance. Standard deviation is always the square root of variance, which is 0.98 something. All right, the next question is asking about the situation that's a 1-in-1. So in contrast, when you're shooting 2 shots, you always take the second shot. In this 1-in-1 situation, you're only taking the second shot if you first make the first one. So let's start off with the same make it miss first split. But if you miss the first one, as in if you're down here, then we're done. If you make the first one, well, then you get a second shot, and that one can also be a make or a miss. So just like before, we can label edges with probabilities, and we can find the total probabilities of ending up with 2, 1, or 0 total shots made. Well, we have a 0.64, 0.16, and now just a 0.2. And just like before, we can find the expected value or the mean of the random variable and the standard deviation of that variable. All right, so this we do the same as before. We're taking the weighted average of the 3 different outcomes, and that should add up to 1.44. The variance we can find this way, just like before. And when we take the square root of the variance, we get the standard deviation, which is the answer that we're looking for. So I just wanted to compare the results that we got in this 1-in-1 case versus the 2 shots case. So notice that the expected value is now 1.44 compared to what it was, a 1.6, right? If in the 2 shots case, the expected value is higher because, you have more chances to make more shots. But I also want to point out that the standard deviation is 0.56 compared to standard deviation here of 0.8. In other words, there is a higher variance. So total expected value of shots is decreased, but there's more variation. And then for part 4, we do the exact same thing that we did in part 2. We are asking what happens if the situation happens 3 times instead of just once. And just like before, the expected value is additive. So since we're doing it 3 times, it's 3 times what our expected value is for one thing. Variance is also additive. And like always, standard deviation is the square root of the variance. Cool. The last question here was, discuss how you expect these values to change if a player's shooting percentage decreased. Well, so naturally, we would expect the expected value to decrease, right? If their shooting percentage is lower, we expect on average them to make fewer shots. But one thing I want to point out is that while the expected value is probably going to decrease if we go from shooting 80% to 40%, the variance and the standard deviation might actually increase. If a free throw shooter is very, very good, as in they always make their shot, they actually have very low variance. It isn't until you decrease that to around something closer to 50%, in which case, it's one extreme or the other, which is a high variance case. Now, once you get down below 50%, as in if you almost never make your shot, you're also consistent, at least. So in that case, you would have a low expected value, but also a low variance, low standard deviation.